So I will talk about the research on biomass valorization, focusing mainly on fast pyrolysis, but I will also talk about anaerobic digestion and other fermentation processes we are working on. So let's start. This is the outline of my presentation. So first I will introduce briefly USFQ and IDEMA and myself. Then I will tell you what is the motivation we have, why we are working on residual biomass and on secondary feedstocks. Then we will go through thermochemical processes, then on biochemical processes, to finally conclude with the final words in future investigations. So let's start. Okay, so presentation. So I think Jose has already introduced USFQ briefly yesterday, but let me show you some pictures and a brief presentation. USFQ has a very nice campus, as some of you can confirm, the ones that have been visiting us, like some people from Purdue, for example. We are ranked as the best university in Ecuador and one of the best also in the region. It is a private university. It is pretty small, actually. It only has 8,000 students. It is based on the liberal arts. So for the American students, it's common to have universities that are focused on liberal arts, but for other regions and for this region especially, it is something very different concerning the type of education we are giving to our students. The chemical engineering department is part of the School of Science and Engineering. The School of Science and Engineering has 11 engineers in 2 sciences. And in our department, we have 13 professors. We have over 200 students that study chemical engineering. We have 8 laboratories for teaching and 8 laboratories for research. And within our department, we have 3 research groups: IDEMA, Grupo de Química Computacional, and the Grupo de Ciencias Aplicadas y Simulación. So these are the 3 research groups. I lead IDEMA, and I will show you what we do at IDEMA. So IDEMA is the Institute for Development of Alternative Energies and Materials. Its focus is on research and development of new technologies for the use of biomass and other wastes as raw material for the production of alternative energies and materials. So Jose has talked to you yesterday about biomaterials, I guess, and maybe a little bit about ethanol production. These are the projects we work together. And I will talk to you today about thermochemical processes and about anaerobic digestion and organic acids. So let's start. These are the main professors that work at IDEMA. As you see, we have 6 professors that work intensely on the experimental work and also on theoretical studies. We work on every scale, from laboratory scale up to industrial design. About my short CV, I studied my bachelor at USFQ, so I'm an alumni from USFQ, but then I did my master's and my doctor engineering in Germany. And after working in an engineering company in Germany, I decided to return to Ecuador in 2007. My research areas are focused on development of new technologies for alternative energies and second generation raw materials, as well as municipal solid waste management and agricultural, agribusiness or industrial wastes, and also on the design and construction of chemical and biochemical processes on any scale. So from my experience, since 2014, I'm the head of the Department of Chemical Engineering. Since 2007, I'm professor at USFQ and founder of the Institute IDEMA. And before that, I was in Germany working and studying, and well, that's it. So let's start with the motivation. Why is biomass and why are secondary feedstocks so important? So let's see. Ecuador, it's a small country, it's not very big. It has a gross domestic product of $200 billion, more or less, in 2019. This year it has been difficult due to the whole COVID situation and so on. But it is a small country. And as you can see in the diagram on the right, the agricultural product is important for our gross domestic product, okay? Mining, manufacturing, especially extraction of oil, refining are also important. But agriculture is one of our strengths. Why? Because we can produce agricultural products the whole year. We don't have 4 seasons. We can have 4 seasons in one day. So we can have from rain and storms up to shiny weather in only one day, but we don't have regular 4 seasons. So we can cultivate all year long. So our agricultural production is 365 days a year, and our waste generation is therefore also 365 days a year. If we see the feedstocks, for example, for biofuels production, we can focus on first generation. For example, bioethanol from corn is a first generation biofuel because you are using the crops of the corn to produce the bioethanol. The same with the sugarcane bagasse in Brazil, or producing from the African palm, producing oils, for example, for biodiesel production. These are all first generation biofuels. They are very useful and they are very good because we are reducing the utilization of crude oil, but we are using the fields to produce energy instead of using the fields to produce, for example, feed, right? To produce food for the humans, to produce feed for animals, to produce raw materials, for example, for fibers or for textile industry and so on. And energy, if you see energy in the value chain, energy should not be put in the first place. Even I can say it, even though I do research on energy, but we don't need such high value materials to produce energy, because you can produce energy basically from everything, right? So you don't need something that is very high value, for example, like corn that you can use to feed animals. You don't need to use corn to produce energy if you can use the residues as well to produce energy, and you don't need the fruit itself, right? So that's why our focus is mainly on second generation. The second generation biofuels are basically the residues or the waste streams or the secondary streams of the agricultural production or of the municipal solid waste or so on. So our focus is on second generation. There is also a third, and also the third generation is about microalgal production, but we will focus now on second generation. So here we have again data from the Ecuadorian agricultural production. As you can see, our main products are our 8 main products: African palm from the oil production, banana, rice, cocoa, sugarcane, forest production, and coffee. So you know, and we are well known for most of them. For example, everybody has seen the Chiquita bananas that are exported everywhere in the world. Also, our cocoa is very famous, and our coffee is also getting more and more famous around the world because we have really good products. And therefore, the residues that are produced with it are also very big. We can see that the main residues is produced by the African palm production, followed by banana, and followed then by rice and cocoa in the same amount. And here on the right, we see which are the types of residues that are generated. So we see, for example, the raki, the husks, the bagasse, they are all high in lignocellulosic materials, right? They are not very high in sugars. They are not very high in starch, for example. They are mainly lignocellulosic materials. That is the residual material. Okay, so we can see here some pictures of the main residues we have been working on. So rice husk, banana spine, sugar cane bagasse, cocoa husk, wood sawdust, coffee husks, palm fiber, palm rachis, and palm nut. So their composition is, as I have already mentioned, it's lignocellulosic material. Mainly it has high amounts of lignin. We see lignin is a complex macromolecular molecule with high molecular mass. We see cellulose in high amounts. We see hemicellulose in high amounts. And we also see, for example, different alcohol monomers and other compounds. So this is the composition of most of the biomass, regardless of the origin. So let's see how is our biorefinery concept defined. Okay, so we all have heard about circular economy concept, where we have a raw material that we produce basic products in the chemical industry, intermediate materials up to the final product. For example, we have a raw material, crude oil. Our basic materials would be the monomers, for example, to produce esters, and then our intermediate materials would be the polyesters, the fibers, to produce textiles, and the final product is our t-shirt for our favorite team. That would be our final product, right? After we use it, or when our team has lost the game, then it becomes a residue. It is a residual material, and what do we do with it, right? So the circular economy concept is based on using this residue as a raw material to go back into the production chain, right? We can do it, for example, I used the example of polyesters. So it is pretty easy to do it with plastics, with material that are from crude oil. It can be recycled because it changes a little bit its properties, but it can be, maybe not in mechanical reutilization, but it can be used especially in chemical valorization, it can be used again, right? But some of it will not be able to be recycled, so it must be disposed. But now let's not talk, for example, about crude oil. Let's talk about agriculture. So we were talking about residual biomass, right? So we have our agricultural production. And from this agricultural production, we produce food and feed for animals, for humans. That is the main goal of the agriculture. And we can use some of these residues to put them inside into the circular economy concept, right? And the final products from our normal circular economy are also used for the agriculture. For example, packages, right, for our food, or fertilizers for our fields. So it is combined within the circular. And if we don't see this disposal to go into landfills or into other waste management systems, but if we see the residues that are produced, especially from the agricultural product, as fuels, we can reincorporate it in the agriculture themselves, right? So we can see here an extended circular economy concept where we use energy, or fuels in this case, as part of the equation, right? So let's see what can we do with the different biomass types, right? So for example, we see, okay, how can we differentiate biomass? The easiest way is to say, okay, dry biomass and humid biomass. It's the simplest way, right? So for example, of production, for example, of fruit pulps or of fruit juices or something, you get a wet sludge with over 15% or less than 15% solids content, so it is very humid. And to burn something that is really humid, it's not very good because you have to dry it first. And when you dry it, you lose a lot of energy just by evaporating all the water, right? And you have dry biomass. This dry biomass, for example, from forests, for trees, this dry biomass can be easily used thermochemically. But if you want to switch the dry biomass into humid processes and the other way around, you will lose efficiency, right? So we will separate into humid and dry biomass. And we'll see, okay, the dry biomass will be processed in thermochemical processes because it is already with very low contents of water. So we will not lose energy in wetting it, in drying it and evaporating all the water. And the humid biomass, it is already in the water phase. So we will use biochemical processes, right? So we have divided into biochemical and thermochemical. So this could be the first decision how you will say, okay, I have a residue stream, will I use be it biochemical or thermochemical. Okay, what is its composition, water content? And then you can decide, okay? The second decision you have to take is, okay, will I work on an anaerobic process, that means without oxygen, or will I work with an aerobic process with oxygen? You have both possibilities. So, and you have both possibilities either for biochemical or for thermochemical. If you go for biochemical, aerobic, you have a called fermentation. Well, it's not 100% aerobic, but it is not 100% anaerobic, like the anaerobic digestion. But you can produce organic fertilizer, you can produce vinous, you can produce bioethanol. Then on the anaerobic side, you can produce biogas by anaerobic fermentation. You can go through this new tendency of acid fermentation. It is not here, but I have to include it. So you can go through acid fermentation. You can go to organic fertilizers. You could also go to organic acids. So it depends on whether you're using aerobic conditions or anaerobic. And for the thermochemical processes, you can go for aerobic. You will have common combustion with energy producing. For example, thermal or electric energy, if you use a water vapor turbine, or you can go into an anaerobic process condition. Used biool, biochar, okay? And the last, if you have, for example, residues with high oily contents, for example, the residues from the palm, African palm industry, right? Then I would go directly into transesterification to produce biodiesel and glycerin. So this graph can be very useful to decide which technology So what have we been working on? Let's see, this diagram is now basically on biomass. We can go into fuels. In fuels, we have worked on anaerobic digestion and alcoholic fermentation, and also another colleague of us has worked on biodiesel. We can go on chemical precursors. If we want to go chemical precursors, we have worked on citric acid. Another colleague has worked on lactic acid and biomaterials, Jose, and we are also working on acid or dark fermentation for the production of volatile fatty acids and later on PHA. Or you can go for the thermal utilization of the biomass, then you can go on pyrolysis. And I cannot see the rest, gasification and incineration, right? So these are the other processes. So you can see, okay, what is the biomass I'm using? What is the final product I want to produce? And then decide which technology to apply. Okay, this is the same diagram, for example, for long hydrocarbons or for plastics. We're working on thermal cracking and catalytic cracking, and well, all the innards you can also reutilize. Okay, so let's start with the first technology. Let's go with thermochemical processes. We will focus now mainly in this presentation on fast pyrolysis, but if you want to work on the material side, you can go also to slow pyrolysis. So what is pyrolysis? Pyrolysis is from the Greek. Pyro means fire and lysis means separating. So it's a thermal decomposition of materials at elevated temperatures in an inert atmosphere. It involves irreversible changes in the chemical composition of organic material. This is very important. It is irreversible, and also the difference between fast and slow pyrolysis is that in fast pyrolysis, the products do not reach thermodynamic equilibrium. So you don't have products that are in equilibrium because the time is too short. So you have other products that what you would have in slow pyrolysis. Okay. You have three products. You have the pyrolysis gases. These are short hydrocarbons mainly. You have pyrolysis oils. These are the liquid products that are not in thermodynamic equilibrium, so they are very interesting. And you have the biochar. This biochar you can use as fuel, as normal char, or you can use it, for example, as soil amendment in the agriculture to return organic carbon into the agriculture production. Okay. So what can you use to do pyrolysis? You can use carbon, you can use biomass, you can use waste plastics, you can use oil, and you can use separated cellulose or lignocellulose for the paper industry or other industries. So it is very flexible on what sources you can use. And it is also very flexible on the products you get depending on the conditions you are working on. So you can get coal and biochar, you can get syngas, you can get short chain fractions, you can get usable oils as chemical precursors, solvents, sugars, and you can get biofuels. Oh, I see the time has passed really fast. Okay, so what are the differences between pyrolysis and torrefaction and cracking? They are basically about the temperature range you're working on. And fast pyrolysis, let's see here, fast pyrolysis is a pyrolysis that is shorter than 5 seconds. So this the pyrolysis where you get the highest amount of bio-oils, as you can see here in this slide here, right? This is the equipment we have at USFQ. It's a fast pyrolysis. It's free-fall reactor. We put here, we have here for solid and for liquid feed. We put the feed in here, and then with inert gas, it goes through the reaction in less than 1 second. And here at the bottom, we analyze all the products and go straight into the gas chromatograph. So this is a project we have been working on with the University of Ghent in Belgium. We have biomass, it must be pre-treated, dried, milled, and so on. And then we do the reaction in the process I showed you, and then we separate all the products and analyze them. Here we have a flow diagram of our equipment. So the most important part is always to see how to prepare the feeding. This is the feeding. We have done the proof of concept with ethyl acetate, a very simple molecule that breaks into ethylene and acetic acid. So we could see, okay, if we are getting the products we desire, if we're getting the kinetics we desire with a molecule we already know and that has been studied before, then we can start working on real biomass that is much more complex and much more difficult because you don't know which product you will get. So for this simple molecule, you can also make theoretical calculus. I see now. To use third, okay. I will go at the end with the question. So here we can do theoretical calculus. So that's why you use chemical reaction engineering. You use the reactor equation to define. And so with these systems, we had defined experimentally and theoretically the activation energy. We have experimental and theoretical, and we have literature values. We obtain conversion, kinetic constants, and yields. Okay, and it's not here. And we have already the first publication on this study of ethyl acetate. Then we have worked with cellulose. Cellulose is a much more complex molecule. We can see it here. With cellulose, we have different products, especially in the liquid phase, the bioliquid. And we have seen that the cellulose fibers are reduced before and after pyrolysis. And so we have used shrinking core model. Shrinking core model is a model that you also learn in chemical reaction engineering. And by using shrinking core model, we can decide whether our system is limited by surface reaction or it is limited. We have seen in our case, it was limited either by surface reaction or by the diffusion of the products. It's interesting because normally you have diffusion of the reactants. In this case, we have diffusion of the products out of the gaseous film. Therefore, we have to solve some differential equations and prepare all the adimensional numbers. So chemical engineering 100%, and we could define the process. And by these diagrams, these are the dotted curves are the theoretical calculations, and the points here are our experimental data. So we see, okay, as we can see, we are on diffusion limiting process that is being limited by the diffusion of the products. Okay, then we kept going with real biomasses. We work with these 8 biomasses that have been fully characterized before our pyrolysis. And then we see which are the yields of every product. We go fast through it. And we can see, okay, for example, from coffee and cocoa, you get high amounts of bio oil. With rice and banana spine, you get high amounts of biochars. for example, in the bio oil of the coffee and the cocoa, you could find theobromine, for example. You can find the active compounds of this biomass. So it's very interesting. And you see in the gas chromatograph all products. And you see also the biochar has changed quite a lot during the pyrolysis. But it is different from each biomass. So it remains a structure, it reduces, it gets more porous, but it remains basically the same structures after and before pyrolysis. Okay, so let me know. It is now 9:30. Should I continue with biochemical process, or would you like to stay here? I can make it also briefly with biochemical processes. Tell me what you prefer.
Well, you have 5 more minutes, and then we have to go to questions.
Okay, so I will make a brief introduction about biochemical. Okay, thank you. Okay, so biochemical, now we were working on high temperature. Now let's switch, it's completely something different. Now we will go with 35 to 45 degrees Celsius. We'll go with high water content. We have about 75 to 80% or 85% of water content in our processes. For example, a good combination is animal manure, because you have there the microorganisms that do the anaerobic digestion, and you have residues from crops or from the agribusiness and go anaerobic digestion. The products are biogas and biofertilizer, and this is done by microorganisms that degrade the organic material in the absence of oxygen, right? This is a brief graphical abstract of a publication about anaerobic digestion. We also, that's something I do in all my research, because I love chemical reaction engineering. That's my favorite in all over the research we are doing. So all my research, there's always something related to chemical reaction engineering. So I have always reactions, and I always want to see, okay, how do these reactions work? How fast are they? How are the kinetics? Are they exothermic, endothermic? Everything about you can find about the reaction engineering. And so we have seen that at different temperatures, you have different reaction pathways, as you can see, because our activation energy changes for a very slow one into a higher one. This is a mechanism that is proposed by the anaerobic digestion model 1. It is now up to anaerobic digestion model 3, I think. And it says, okay, the carbohydrates, proteins, lipids from regular residues, they are degraded with acidogenic bacteria. Well, first they are degraded by hydrolysis. It's fungi, and they are degraded into amino acids, sugars, fatty acids, and alcohols. And then these shorter compounds are degraded with acidogenic bacteria into propionic, butyric, and valeric acids. These short chain acids are then degraded with acidogenic bacteria into acetic acid and CO2 and carbon dioxide. And then for the methanogenesis, you use archaea. It can be either acetoplastic or H2 consuming methanogenic archaea to produce the biogas. So this is the conventional process for anaerobic digestion and biogas production. You can cut it at this stage here after the acetogenic if you want to produce short chain carboxylic acids. They can be used as feed, for example, for agar production. I read someone asked about agar production. So this can be used, for example, into algae production streams. So we work on laboratory scale reactions, pilot scale 400 liters, and we have also designed and constructed an industrial scale anaerobic digestion plant that is working with residues from a fruit processing industry. So we have fruit processing, fruit wastes that are high in sugar content. It's perfect for anaerobic digestion, okay? Then we work with bioethanol production from lignocellulosic biomass. As I mentioned before, lignocellulose is the highest content of our residues. So it is a little bit more difficult than to produce bioethanol from sugarcane, from the sugar mother liquid than from the lignocellulosic biomass, but we're working it. It's basically on the decision on the chemical or enzymatic hydrolysis. So we are getting pretty good results. We are also working on citric acid production. This is a process we work with Aspergillus niger. We have worked with 4 different strains. 3 of these strains have been isolated here at Ecuador, so they are local, and 1 is the industrial strain. So we want to see if we can get strains that are equivalent to the ATCC strain, commercial ATCC strain, to produce citric acid. We can also use biomass, for example. It's an interesting example as adsorbents. It is very funny because in the crude oil extraction industry, they use a lot of water that is being injected into the ground to get the oil out, right? And this water has to be treated because it ends up really contaminated with surfactants and with the oil residue and so on. And so for this treatment, it is one of the steps, or the final step is normally an adsorption step. And for this adsorption, companies import into Ecuador walnut shell, the normal walnut that you use in Europe and in the States. We don't have walnut production in Ecuador. And so they import containers full of the walnut shell. Can you imagine? It's a residue in other parts of the world. And they use it to do the adsorption of these contaminating hydrocarbons. And so what we were using is, okay, we have enough, or we have different residues of biomass that we can use instead of importing walnut shell. So we have found that there is some biomass that can be used as adsorbents also here locally. This is also cracking. This is not more biomass, but it's other processes. For example, we use motor oil, and with plastics, we are using also PFRs here, and we are producing synthetic diesel. Okay, so let's finish with it. What would be the conclusions? Fast pyrolysis is a very interesting process where you can get the bio-oil as the product of interest. The next step is to see how we can use this bio-oil, because it is a combination of a lot of compounds. Will we use it, for example, we can use the bio-oil as raw material for biochemical processes because it has high sugar contents? Or will we use the bio-oil and put it into an extraction to get the compounds of interest out of the bio-oil? So it is still under debate, how will the bio-oil be used? And it's a debate that is going now worldwide. Well, then the percentage of liquid weight, the different products. Here we have levoglucosan. This is one of the very interested products because it's a sugar that we can use for biochemicals. Then we are working, what is the future investigations we are doing now at IDEMA? We're working on fast pyrolysis of plastics. This is where we get our smiley. As you can see here, we have during our SEM images, we have found a smiley. So we see this is a research that is smiling at us. We are working also on other model molecules like aspartame. So we want to see how amines are forming and are being degrading into pyrolysis products. And as a general message, I want to just tell you, energy is, if you have to define the value chain of products, you should choose energy not as the first option, but as the last option, right? Because you can produce energy either from first generation, but you can also produce energy. It will not be degraded. The energy is still, the quality of the energy is the same, either you use first generation or a main product, or if you use it from a secondary stream. So if you have to decide future in your professional life, which energy source to use energy always as the least value chain product, okay? Chemical precursors is much more valuable. You can use the biorefinery concept. You should use the biorefinery concept to produce chemicals, green chemicals. And biomaterials is also something that is very important to produce, because you can use from biomass into scaffold matrix. Filtering material is something we're starting to work on. So that would be the message I wanted to give to you. And thank you very much for your attention. And I'm here for any question you might have.
Okay, thank you for your presentation, Dr. Almeida. Now we will move on into questions. So the first question is, why did you decide not to use third generation biomass?
Because you have to have algae production before you can use it, this algae, to produce energy. And the algae production by itself, it's something we want to work in the future, but not for energy production, but to use algae, for example, for chemical precursors, because you can from microalgae produce bionylon, you can produce PHA. It's something we are working now. We are starting to work with dark fermentation to use the products of the dark fermentation into microalgae production, and then to produce green chemicals. That's what we are interested in. And then the residues from the microalgae production you can produce for energy production. But there has been studies, I think the last 15 years, where they wanted to produce direct high lipids microalgae with high lipids content to produce biodiesel out of microalgae, and it has not shown to be efficient, because the production is very low. So I think direct biodiesel production from microalgae is something that has not been really going through. Besides, it has been studied for over 10 years. But to produce green chemicals from microalgae is something very promising that we will start working now on this year.
Okay, thank you. Now, next question is, which percentage of the energy requirements in the country do you believe the mass scaling of biomass use will suffice, with the amount of residual biomass being produced in Ecuador?
Yeah, it's not very high. I don't have the numbers now in my head, but it's not very high. In Ecuador now we have in Ecuador over 80% of our energy is renewables, but it is hydrothermal, because we have a lot of hydrothermal plants. So we're using our water resources for energy production. The bioenergy from biomass, I think it's now between 2 and 3%, considering biodiesel and considering bioethanol production but first generation and second generation. And we will be glad if we climb up to 7-8%, but it's difficult to go higher. Even for example, even Germany, that is a country that is very high on renewable energies, can't go above 14% with biomass. So the percentage, if you see percentages, it is still very low.
Okay, thank you. Now, next question is, what do you think will be the reach of biofuels and bioreactors in Ecuador and Latin American region in the next decade?
Very important. For example, if we consider chemical precursors, okay, if we consider green chemicals, I think it will be very, very, very promising. There are a lot of interest for new research groups that are now working on biomass valorization. And chemicals, biochemicals, green precursors, biomaterials is something we can really rely on, and we can start developing. So I think in the next decade they will develop quite a lot.
Thank you. Now, next question is, what do you think about the EROEI of biomass-Pyrolysis biofuel, as it needs a higher energy? It's the last one.
Okay, EROEI of biomass biofuel. You will have to Manav, can you please explain what the abbreviation for EROEI is? I don't know it. It's maybe an acronym we are not used to. Estimated return of energy in, okay, good. It on all renewable energy products, the return of investment, if you see energy alone, it is not feasible. The processes are not feasible. We have calculated a lot of different processes, either of pyrolysis or anaerobic digestion. So if you use only one product, the energy, the processes are not feasible. You have to put 3 different products or three different benefits. Then you get the products that are feasible. First is waste management. So if you consider the costs related to waste management of landfill production, greenhouse gas emissions, water contamination due to leachate, it is difficult to put it into monetary values. But if you consider the waste management streams, or at least the waste management, the reduction in the costs into the waste that are being translated from landfill into value. So the reduction in landfill, at least if you consider this, then energy, of course, and then if you can find another product of interest that you can sell. For example, in the fast pyrolysis, you can consider biochar. It is a product that the agriculture needs. It has low price, but it is a product by itself, so you can sell it. So if you consider these 3 prices or these 3 products, then you get feasible projects. Otherwise, if you consider only energy, the problem is in Ecuador and in many other countries, energy has a I don't know, how do you say it? Subsidium? It's subsidized, right? It is not, you are not paying what it really costs because the government is taking part of the costs for energy. And the high energetic plants, it's either thermoelectric or hydroelectric plants, they are calculated for 30 years of use. So the cost for the return of investment of such plants are very, very slow. And if you have, especially in Ecuador, for example, in many countries, these projects are normally private. They are not financed by the governments. And so you have to have a return of investment of maximum 5 years. You cannot say, okay, I will pay the investment in 10 years because you don't know what will happen in 10 years. So in countries like ours, where you have high uncertainties, you have to have a return of investment of maximum 5 years. And so if you rely only on energy, the projects are not feasible. And that's why it has been so difficult to implement such projects here. But if you see, okay, we will not only consider energy, we will consider, okay, let's see, in Ecuador, the real cost of a ton of waste should be around $200. Okay, nobody pays that amount. The end user, we don't pay it, but it is subsidized again, and the municipalities pay around $200 per each ton if you consider all the years that have been post-treated, then with the biogas utilization and leachate treatment and so on, it's around $200 per ton. If you consider this $200 per ton that are not going into landfill, and these $200 are going into the investment of this renewable energy plant or on this pyrolysis plant. And if you consider the energy, and if you consider selling, for example, biochar, then you get a process that can be feasible, and you can get return of investment of less than 5 years. And you have to guarantee less than 5 years in Ecuador to have a process that will be invested on. If you have something that will not be invested in, and you will not get return of investment in less than 5 years, nobody invests here. That's the reality. It's different in the US and in Europe, where you can really have projects on long perspective, and you can have, okay, let's see, 10, 15, 20 years of return of investment. That's no problem, because you have countries that have stability. But in our countries, I think in all Latin America, you have to have short return of investments. That's why our countries are so expensive, because we cannot rely on what will happen. When will we have the next elections, with next president, with new philosophies, and everything will change. So it's difficult. I hope I answered your question.
Okay, so now the last question. Are catalysts often used in fast pyrolysis and other biomass conversion reactions, for example, ethyl acetate pyrolysis? If so, what are the desirable catalysts and why?
Okay, you use the catalyst in the second, when you use catalyst in pyrolysis, you use in the second step. You first use thermal conversion. So you have a first degradation, and then you put a catalyst on the second step. It can be really connected online, so you actually don't notice. And in the second step, you convert the products into the desired products. We have not worked yet with catalysts on pyrolysis, but we have worked with catalysts on catalytic cracking, for example, for plastic and for used motor oil. We have worked with aluminum silicates. They are mesoporous aluminum silicates doped with different metals. For example, we have seen that nickel is very good catalyst. So aluminum silicates with nickel doping is very good for catalytic cracking. It's for shortening molecules. So I don't see the questions. Which molecule were you interested in? Normally for organic acids, you try to work with silates. Silates are very good, and other oxides, for example, vanadium oxide or zinc oxides, they work pretty good normally. But as I mentioned, for pyrolysis, you have the two steps. First steps is the thermal degradation, so where you can shorten the first molecules, and then you have the catalyst reaction, where you can put the catalyst to get the product, higher yields of the products that is desired.